proton and a neutrino of the electron type. We have a lot of thorium and uranium present in the Earth's crust. That also results, and this is what we call as geoneutrinos. Then, of course, we have the solar neutrinos, and we know that the PP chain, which is 98% responsible, and the CNO cycle, which is just 2%, are the two major fusion chains producing energy inside the sun. And this is how the reaction goes. 4 protons fuse together to form a helium nucleus, and 2 positrons, and then two neutrinos of the electron type are emitted. In all my slides, I'll be showing the neutrino or the anti-neutrino, the blue font. So from the sun, we have about 2 into 10 to the power 38 neutrinos of the electron type which are produced per second. If we see an energy distribution, about 6 into 10 to the power 10 per centimeters per second in the energy range of less than 0.42 MeV, and about 5 into 10 to the power 6 per centimeter square per second in the energy range of 0.8 to 15 MeV reach the Earth's surface. What does that mean? It is about 65 billion solar neutrinos per second passing through every square centimeter perpendicular to the direction of the sun, and this is a huge number. So what happens, suppose a neutrino is produced inside the core of the sun. It takes 6 seconds to escape the sun's mass, whereas photons, it may take about 2 into 10 to the power 5 years to escape out of the sun. It's just because of their interacting nature. Then we, of course, have the atmospheric neutrinos. Now, neutrinos are also produced when high-energy cosmic rays, primarily the protons and light nuclei ejected from violent stellar phenomena, scatter hard on the nuclei of the upper Earth's atmosphere. We know this phenomenon very well. Now, this is the multi-step process in the sense that the first scattering produces pions and kaons, and with a preference towards the positively charged particle. These charged pions and kaons then decay to muons and muon neutrinos, and these muons then decay to electrons and both muon and electron neutrinos, as we see in the equations here. So it's a two-step. First, the pion is produced, and then the muon decay results into the observance of this neutrino and antineutrinos. The spectrum of these neutrinos range from about 30 MeV to 3000 GeV, with a flux of about 10 per centimeter square per second. The first known account of atmospheric neutrino detection was from the Kolar Goldfield experiments in India, parallelly with the ERPM experiment in South Africa. So this slide number 18 basically shows the natural source of neutrinos through a pion decay. So a pion basically decays into a mu plus and a neutrino of the muon type. And in the next slide, we see how the muons decay, the mu plus and the mu minus, resulting into pairs of neutrinos and antineutrinos. So what we see is that all muons decay to at least an electron and 2 neutrinos. Then, of course, we have the supernova neutrinos. Neutrinos and antineutrinos of all flavors and covering a range of energies of about 10 to 30 MeV are emitted when a star with a mass enough more than 1.4 times the solar mass undergoes supernova explosion. This is the Chandrasekhar limit responsible for the explosion of the supernova. Beneath this, of course, they turn into white dwarfs. So these neutrons carry almost all the energy of the explosion, and about 10 to the power 58 of these are emitted within a time period of just 10 seconds. And they are very helpful in understanding the dynamics of collapse from very early on in the process. For example, the supernova of 1987 that occurred in large magnetic cloud within our galaxy was observed by the atmospheric neutrino detectors. About 25 neutrino events were registered across 3 different detectors within 12 seconds and helped confirm our basic understanding of the supernova phenomena. This was in 87. However, the explosion had occurred about 160,000 years ago. Then we have the accelerator neutrinos, and bombarding of high energy protons from accelerators onto low Z targets produces high energy pions, which can then be focused and allowed to decay into muons and neutrinos of the muon and electron flavors. An array of high Z absorbers can then stop these muons and produce a pure beam of neutrinos. And certain accelerators are being designed around the world. And anyway, the existing accelerators also keep on producing neutrinos and antineutrinos. There is some contamination of the electron flavor neutrinos, but that can be accounted for by using a near and far detector. This type of things you've seen in many of the experiments which are being planned around the globe. So neutrinos of energies ranging from 30 MeV to 30 GeV can be produced through accelerators. And then the last, I'm coming to the nuclear reactors. The core of a nuclear reactor is the most abundant man-made source of neutrinos. A standard 1 GeV electrical power output reactor can produce about 10 to the power 21 neutrinos per second. It should be anti-neutrinos. As all of the neutrinos are from the beta decay of daughter products of fission, no other flavor of neutrino is produced. Hence, there is no contamination in case of nuclear reactors. The neutrinos, the anti-neutrinos coming out of the reactor. The flux of these neutrinos extend only up to about 8 MeV of energy, with where the statistics after which becomes quite negligible. On slide 23, if the slide 23 is being displayed, just I want to have a check here.
Yeah. This is fine.
Yeah. So here we have on the x-axis we have the neutrino energy and the flux on the y-axis, and as we see that these are the total type of neutrinos, and with respect to the energy and flux, we have the cosmological neutrinos, the solar, the supernova, geological, the power plant neutrinos, and this is the basic talk of today, which we'll be discussing, and this is how the flux varies. Now, this map on slide 24 shows the experimentally determined geoneutrino flux around the world, both from the natural decay of uranium and thorium in Earth's crust and mantle, as well as the man-made reactor neutrinos. So you can see almost everywhere we have the neutrinos bombarding us, from outside the Earth, from the atmosphere, and everywhere. A neutrino oscillation phenomena. This is a bit conceptual. I will spend a little time on this just to gel the things and would not go into the details of how things have been arrived at. So what happens, I'm just trying to give an analogy here. If we have identical pendulums, as we see on the top figure, and they have the normal mode, then that generates the low frequency. But these two identical pendulums can also oscillate in different directions, and then it's a higher frequency. And these pendulums are having the same mass, same length, everything is similar. What happens when you have two pendulums of different masses, M1 and M2? The lengths are also different, L1 and L2, which result in a different θ1 and θ2. Then they tried the time evolution of the pendulum. If you see, you will have like this, the red one oscillating and the blue one on the bottom, what is shown. So neutrino oscillations are from a mixture between the flavor and the mass eigenstates of the neutrinos. And we know right now we are talking about only the three flavors, the electron type, the muon type, and the tau type. So neutrinos are created in weak processes in their flavor eigenstates. Neutrino oscillation arises from a mixture between the flavor and mass eigenstate of neutrinos. As a neutrino propagates through space, the quantum mechanical phases of the three mass states advance at slightly different rates due to the slight differences in the neutrino masses. This results in a changing mixture of mass states as the neutrino travels. But a different mixture of mass states corresponds to a different mixture of flavor states. So a neutrino born, say, as an electron neutrino, will be some mixture of electron, muon, and tau neutrino after traveling some distance. It is because the mass differences between the neutrinos are small that coherence length for neutrino oscillation is so long, making this microscopic quantum effect observable over macroscopic distances. So what happens? Let's understand what is survival probability. A pure beam of electron-flavored neutrinos has a survival probability which oscillates due to M1 minus M2 mass difference. For a single neutrino energy E nu in MeV at a distance L from the source, the survival probability can be given in terms of the mixing parameters sine square 2 theta and delta M square, which is M nu square minus Me square. These are some concepts which are used in explaining oscillation phenomena, and this is how the probability is given of the probability of an electron type of neutrino surviving as an electron type as 1 minus sine square 2 theta, and this is the equation in which delta square is in EV square, length is in meters, and MeV or length can be put in kilometers, and the energy in GeV. So on slide 29, if you see this formalism, the theta is the oscillation amplitude is controlled by the mixing angle theta, whereas delta M square that you see, this is defined the frequency of oscillation and is proportional to delta M square. So these are two important parameters in this. And experiments search for excess of the muon type of neutrino in a beam of electron type of neutrinos, and the amount of appearance may then be used to infer limits on delta M square and sine square 2 theta. Now for solar neutrinos, L is large, and therefore the sensitivity in delta M square is small, 10 to the minus 5 to 10 to the minus 10 EV square. This is the low frequency. For cosmic neutrinos, L is small, and the sensitivity in delta m square is about 10 to minus 1 to 10 to minus 3 V square, whereas for reactor neutrinos, L is the smallest, and the sensitivity in delta m square is largest, about 0.1 to 1 electron volt square, and this is the high frequency. In order to measure small neutrinos, one need to know at large L, which is the baseline. So a little bit about the solar neutrino oscillation, because this has been resolved. So let us understand what happened if this, what was the anomaly and how it was resolved. And then we will go to the reactor neutrons. So neutrino oscillation is a quantum mechanical phenomena whereby a neutrino created with a specific lepton flavor will be measured to have a different flavor. The probability of measuring a particular flavor of a neutrino varies periodically as it propagates. We have understood this so far.
Lalit, can you hear me?
Observation of the oscillation. Yes.
Lalit, can you hear me? Your voice is a bit.
Yes.
I'm wondering whether
Yes,
if you can, if there's some sitting position or coming closer or something, if that helps.
Okay, I'll try to come closer. But since how long was that?
Yeah, it's going on, but of course, with a little bit of difficulty, we are able to follow. But I'm just wondering if it can improve.
Okay, I have come closer to my.
Yeah. No, 31. I mean, this looks fine as of now. So maybe if there is any further problem, I will interrupt you. I'm sorry.
Okay, sure.
Yeah.
So I'm at slide number 31.
Yes.
And the observation of the oscillation phenomena implies that the neutrino has a non-zero mass, and this is for this reason it is not a part of the original standard model of particle physics, because in that standard model the neutrino is supposed to be massless. So what happened to the solar neutrino problem? The measured flux from the sun was found to be 1/3 of the expected flux, and this is the story in 1960. What you are seeing on the right side is the Sudbury Neutrino Observatory, in Canada. This is about 2 kilometers underground in a nickel mine, and it is having about 1 kiloton of D2O to be used for detection of the. Basically, it was designed to explain the anomaly. So Sudbury Neutrino Observatory suggested that a fraction of the electron neutrinos produced by the sun are transformed into muon neutrinos on their way to the Earth. And this was quite a big engineering feat, because you see about 500 people had been working for almost 24 years. So what they did, I think in the right side there is the D2O, which is about 1,000 tons, and that is surrounded by H2O. So the Sudbury Neutrino Observatory provided a means to measure both the electron and the non-electron components, and the presence of the latter showed that neutrino flavor conversion was taking place, a hallmark of neutrino oscillation in mass. So we have two boundaries here, as you see, the D2O and the H2O. Why it was designed like that? Because there is elastic scattering which happens, and the neutrinos of all the flavors is put as nu X. So all the three flavors can participate in that, and rates are similar both in H2O and D2O. Whereas the neutrino in the deuterium can interact with both the types of neutrinos. So in case of an electron neutrino, it produces the charge current. Okay, so this clearly shows that only electron type of neutrino can participate, whereas the deuterium also interacts with the other flavors, and so that is called the neutral current. So by measuring the charge current and the neutral current and this elastic scattering, they could find out that in case of the 8 boron flux from sun, the flux of the charge current was much less than that of the elastic scattering. So at Sudbury Neutrino Observatory, heavy water target was used to study the neutral current and the charge current scattering of deuterium in addition to the elastic scattering process, and that it was concluded that neutrino oscillation is responsible for observation of neutrinos other than the electron neutrinos. A similar thing for atmospheric neutrinos was done at Super Kamiokande, and this is again a 1,000-meter deep lab and having about 50 kilotons of pure ultra water. And the same thing it did, and now the energy range of the atmospheric neutrino was different. It was from few emissions to few TeVs. And so I'm just showing all this just because these are experiments which is sort of benchmarked the oscillations in the atmospheric neutrinos as well as in the solar neutrinos. And this was the first experimental evidence for atmospheric neutrino oscillations in 1998. Now, what basically happens, this is the last slide on this. When you have muonic interaction, a muon is produced, and you see it's a charged particle, and then you have a Cherenkov cone which is formed, and it remains more or less steady. Whereas in case of the electrons are much lighter than muon. Wherever the electron neutrino interacts, the electron basically wavers, and so you have the Cherenkov radiation from the electron shower produced by an electron, and it is basically a diffused cone. And as you could see in the previous slides, we had the photomultipliers all along, and they were used basically to decipher this muon and electron contributions. So much about the reactor antineutrino, about the oscillation phenomena of the neutrinos. And now I move to the reactor neutrino oscillations. Now, anti-neutrinos from reactor provide an excellent non-intrusive probe for monitoring reactor power and its core composition. The detection of antineutrino through the inverse beta decay at closer distances, about 10 meters or so, would be interesting for the sterile neutrino searches. These are two physics motivations. I'll come to these things now one by one. Now, if you see this slide, on the x-axis, we have a reactor distance from the reactor. Basically, it's not a distance from the reactor, it is a distance from any source which is producing the neutrinos. But here, since we are dealing reactors, so we call it a reactor detector distance in meters. And it's on a log scale. As you can see, it goes up to almost 10 kilometers and much beyond that, up to 100 kilometers. On the y-axis, if you see, it's the ratio of the observed to predicted neutrinos. Now, if there are no oscillations happening, then you will see a dotted line on the top, what you see right now at 1. The ratio of observed to predicted has to be same, so it will be 1. What happened? Now, if you see at large distances, there was a solar neutrino anomaly, which was resolved. Then, of course, you have the atmospheric neutrino anomaly at about distances of about a kilometer or so. Now, what you see here, there are two types of curves which are shown. One is in the gray color, which is dotted. So in that, the 3 neutrino flavor was taken, and it could nicely explain the oscillations of the solar anomaly as well as the atmospheric anomaly. So 3 flavors, the electron, muon, and tau, could nicely explain this anomaly when the flavors were changing from one to the other. And then it merges nicely with the curve at 1. But when we come to closer distances now, when 10 meters or within 100 meters, we see a lot of discrepancy in the data which has been collected, of course, with very large error bars. So this is what is the reactor antineutrino anomaly. You see that they certainly do not come at 1. And the fourth flavor was therefore initiated to whether that can explain, and that fourth flavor is the sterile neutrino. And we can see that the thick black line is able to explain the data. Of course, the data is having very large error bars, but then the fourth flavor nicely goes, and then it finally merges at 0 to 1. So this is the area which is called terra incognita, and about 20 projects are running right now. And we have Smaran detector basically to look into a distance from say 8 meters to 15 meters, whether we can also look in both into the sterile part. But before the sterile part, we have to really make the detector work, whether we can reproduce the antineutrino spectra from the reactor. Sterile neutrinos, inert neutrinos, are those that do not interact by any of the fundamental interactions of the standard model except gravity. The term sterile neutrino is used to distinguish them from the known active neutrinos in the standard model, which are charged with the weak interaction. They may, however, be responsible for a number of unexplained phenomena in physical cosmology and astrophysics, including dark matter. So I come to the reactor monitoring facilities around the world. 2 facilities I'll just discuss here, the SONGS and the Nucifer, before I come to the ISMARAN. The International Atomic Energy uses an ensemble of procedures and technologies collectively referred to as the safeguard regime to detect diversion of fissile material from still nuclear fuel cycle facilities to weapons program. IAEA interest is the reactor safety operations based on neutrino detection. Anti-neutrino flux is directly related to the fission process or the core composition. So the reactor neutrino monitoring has the potential to non-destructively measure the plutonium amount in the core. So this is the motivation, what IAEA suggested to chart a path to sequence deployment based on neutrino detection, anti-neutrino flux related to fission process in the core, real-time information on isotopic fission rates. Anti-neutrino flux cannot be controlled or shielded. It's non-intrusive, continuous, and remotely operated method. So the specifications laid down are that it should be a safe and robust, a compact, easy to use even by the non-neutrino experts, and can be remotely controlled. If this method proves useful, IAEA has the authority to request any nuclear power plant to be controlled with anti-neutrino monitoring temporarily or permanently. So what happens in a reactor? You know it's a thermal neutron induced fission, 235 uranium to the fission, and through a sequence of beta emission, about 6 beta particles are emitted in per fission of uranium 235. So it has the proportionality with the power. If we have a 1 gigawatt thermal reactor, it produces a 2 years amount of anti-neutrinos, as you see, 2 into 10 to the power 20 anti-neutrinos per second. So 6 anti-neutrinos per fission and about 2 into 10 to the power 20 anti-neutrinos per second from a 1 gigawatt reactor. What does it mean? 5% is radiated away as anti-neutrinos. The average nuclear fission releases about 200 MeV of energy, of which 4.5% is radiated away as anti-neutrinos. Means if you have a typical nuclear power of 4,000 megawatt thermal, and with the efficiency correction, it translates to about 1,300 megawatt electrical. The total power production from the fissioning atom is actually 4185 megawatt, of which 185 megawatt is radiated away as anti-neutrinos radiation and never appears in the engineering. That is to say, 185 megawatts of fission energy is lost from this reactor and does not appear as heat available to run turbines, since anti-neutrinos penetrate all building materials practically without interaction. So I'm at slide 47, and this is quite an interesting slide. The first observation of neutrinos in the time period of 1953 to 56. Rhines and Cohen's performed experiment at Hanford Nuclear Reactor in 1953, and later in 1955 moved to the Savannah River plant in South Carolina. Now, Rhines won the Nobel Prize. This is the strangeness of this Nobel Prize committee, that whosoever dies, they don't give the Nobel Prize to them. And Rhines won the Nobel Prize, but Cohen had died by the time, so Rhines got the Nobel Prize. And they had used a liquid scintillator to basically detect the anti-neutrinos coming from the reactor. This is stories of 1956 when it was discovered. So what happened, if you see on the right side, on the bottom, we have an anti-neutrino which comes and hits a proton. This proton is in the liquid scintillator, as was used by Rhines and Cohen's. And then it produces a positron and a neutron. The positron, being lighter in mass, carries maximum energy of the reaction, and it deposits its energy d by dx in the medium, and towards the end of its range, it will get annihilated with an electron and produce 2 photons. And this is the prompt part of the reaction. This anti-neutrino is detected indirectly. Now, what happens to the neutron? The neutron goes into the medium of the same plastic scintillator, gets thermalized, and then in the liquid scintillator, it was doped with gadolinium. So gadolinium has a huge capture cross section for thermal neutrons, and once neutron is captured, it produces a cascade of gamma rays of about 6 to 8 MeV. And this is the delayed process. So you have a prompt signal and you have a delayed signal. And if you can establish the correlation between the prompt and the delayed signal, you can say that you have discovered the anti-neutrino. So the prompt signal, the positron kinetic energy and the gammas from its annihilation produce an initial prompt burst of light. This is very fast. The delayed signal, the neutron energy is small and it bounces after microseconds. Now it depends what type of scintillator you are using. If you are using a liquid scintillator, it is typically of the order of about 30 microseconds or so. And it is then captured after thermalization by an atomic nucleus. It can be captured by hydrogen as well as gadolinium, but gadolinium has a very large capture cross section, and producing gamma rays as the nucleus releases excess energy of about 8 MeV. So about 76.9% of the neutron capture on gadolinium, which have about 10 to 5 times larger thermal neutron capture cross section than hydrogen. So a coincidence was set up. Rhines and Cohen found that the delayed coincidence of the two signals separated by characteristic time lag would greatly reduce the experimental background, making it possible to use the less intense neutrino flux from a nuclear reactor. So this is the shape of the neutron energy spectrum via inverse beta decay. anti-neutrino arms interact with the proton and produces the positron and the neutron. The masses are quite different. Positron is the lightest, carries away the maximum kinetic energy. Neutron is the heaviest, moves with a little bit of energy of reaction, and finally gets thermalized and gets captured. So we have a flux, the anti-neutrinos, and we know the cross sections are very small, 10 to the power minus 42. So it's a very, very small cross section, but then we can have a reasonable interaction rate if we have a large detector which can provide the interacting nuclei. So if we just count the neutrinos per day, it is directly related to the power of your reactor, and it is rated like this, the target mass and the power of your reactor. So we can have a reasonable count rate in a day if we can design such a detector. So what we have done. So before that, I'll just show you the same thing in a different in a calculation. We have 1 ton of target at distance of 25 meter, and suppose the reactor is 1 gigawatt, it will give rise to 4,600 interactions in a day. Now these interactions are with the hydrogen present in your target, which can be a liquid scintillator or a plastic scintillator. So you have about 4,000 interactions per day and 1% statistical error within 2 days. You can generate this with a statistical significance, and you can say that yes, you have detected an anti-neutrino. Just 2 experiments I will refer here very quickly before I come to the Ismaran. One is the songs and other is the Nucifer. I will just show the results and what type of detection technique they had used. So this is the Song San Onofre nuclear generating station in US. And as you see here, this is the reactor core, and at 25-meter distance, they have planted in the basement. And this is crucial because once you are inside a reactor, you need quite an amount of shielding so that you do not interfere with the neutrons and gammas which are already present in the reactor. And you will see what are the challenges we have with this when we show our results. So this is very well shielded in the basement, and it's at 25-meter distance. This is a 1 gigawatt electrical reactor, detection efficiency of about 100%. And this is the liquid scintillator that they had used along with the muon veto shields. The muon veto shields are in brown in color, and they had slabs of liquid scintillators. And as you see here, this is what they had on the black one is the reactor power. And there was a 250 kilogram of a 1.5 ton of fresh uranium which was refueled, and you can see the experimental points on the red line which clearly match with the power going down and then the power coming up. And of course, they can tell you that even they can tell you the content of the uranium and plutonium in the reactor. So I move to the next one, which is the Nucifer in France. If you can see on the top left, again, this detector is embedded inside the reactor in a basement and very well shielded with the concrete and other things. This is a very compact core reactor with about, as you can see, 57 into 57 into 60 centimeter cube. And it's an enriched core. But again, you see, you have about 1 ton of liquid scintillator and a distance of 7 meters. This is the closest an experiment which we can see, which is very, the closest to a reactor core. But the material that is used is again liquid scintillator, which is about 1 ton, and the heavy shielding you can see on all the sides, which consists of verted polythene and lead and whatever it is required to shield the background from the reactor itself. This is another picture. And so the total accumulated weight of the whole structure, including the detector and basically to the weight of the shielding, it comes to about 50 tons. And so here is how the reactor has been monitored. It is a 70 megawatt reactor, and you can see where the reactor goes down just by measuring the antineutrinos, and you can just tell about the reactor operations. And of course, here they are doing the neutrinos from the uranium and plutonium. So now I come to the Spuran detector. We have chosen a plastic scintillator for the reasons that there are certain advantages with plastic scintillators. It improves the safety characteristics, makes deployment and operations easier. And we are sea level operations. When you place in a van outside the reactor, it is non-inflammable and do not have to use a separate muon detector in this case of a plastic scintillator. There are disadvantages with liquid scintillator. First of all, it's not available so easily. There are security issues related to toxicity and flammability, and the chemical compatibility with the container wherever they are put into, and need complicated retaining structures and have to go for an underground deployment. So this we have seen. If we know the fission happening in a reactor, how to calculate the number of neutrinos. These are the numbers which we have fed, how many number of protons we have, what is the detection efficiency at 15%, and we are at a 13-meter distance from the reactor core. And we know the power which through reactor operates at 100 megawatts. And we know the flux average cross section and the average energy per fission. So based on this simple calculation, the expected anti-neutrino rate is about 60 per day, where a point source has been assumed in the calculations. So this is the pictorial representation. This was the conceptual design of how we will build the reactor. What you see inside, these are the 100 plastic scintillators, which are read by photomultipliers from both the ends. And then they have an immense shielding of lead and then braided polythene, and on the top you have the muon veto detectors. The entire thing weighs something close to about 16 to 18 tons, and this is the engineering drawing of the same thing, which is being fabricated in CDM in BARC. And as you can see, the muon detectors are on the outside with the red color. Inside you have the core detector and it's shielded nicely with lead and braided polythene. These are the simulations by a group to really come out what type of thickness is required, because we can't afford to put an infinite thickness because it has a weight and there's a load bearing capacity of the floor. So we had optimized with 10 centimeter of lead and 10 centimeter of braided polythene. Braided polythene basically to stop the neutrons in the reactor environment, and lead for the gammas which are there in the reactor. So these were optimized. And as you see here, this is the full scale engineering drawing with the core detector, the lead shielding, which is in green, and the braided polythene, which is on the outside. But finally, what happened, we had to change the matrix to 9 by 10 because we realized that online we will have to do some calibrations. So we had to insert some devices so that periodically we can calibrate the detectors. And because of that, we had to change the matrix from 10 to 10 to 9 by 10. And but we have seen that there's not much loss of efficiency in such a rearrangement. So the current status of experimental facility at Dhruva, these are the simulations where you see the neutron capture time plotted for a full scale Smaran for 100 scintillators. And this is the capture on the gadolinium and hydrogen. You can see the difference here, and which gives the characteristic time of about 68 microseconds. And these are again the simulation studies in which the positron energy spectrum is plotted with different thresholds. And on the right side, you see the multiplicity on how many bars are associated with that in detecting the positron. Then we have, so this is the prompt signal. As you know that positrons are associated with the prompt signal. And then of course we have the delayed signal with respect to the neutron. And again on this slide, you see the sum energy, the multiplicity in the number of bars. And so a delayed event in Smaran is defined as energy deposited by cascade of gamma rays from the neutron capture on gadolinium or hydrogen. So this is the basic element, one scintillator you see here, which is read by photomultipliers on both sides. And to make the system very compact, we have digitizers which we are using. And these are the waveform digitizers, 500 megasamples per second. So all pulse processing things are removed in between. So you have a signal coming from the photomultiplier which directly goes to the digitizer. And so the things become very compact and neat. And then we do an offline analysis. So before drawing all these things, we had calibrated each detector, seen its, we have to calibrate, and then you see here with various radioactive sources it has been done, cesium, sodium, cobalt, americium, beryllium. And then of course on the right bottom part you see even the muon background has been measured, which is close, the bump is at close to 20 MeV in this 10 centimeter thick scintillators. In this slide, you see different techniques which were evolved to decide about the prompt and the delayed event. I will not go into the details of this, and this took an enormous time because the people who are working on this, they really have put a lot of time to arriving at these numbers. So now I show you the mini Smaran from which we had some data, and this mini Smaran basically consists of 16 scintillators, because till that time we did not have the full 100 scintillators with us. And so you see, this is how it was being built inside the reactor hall of the Dhruva reactor. And so you have the lead here, and beneath lead you have the braided polythene, and these are the 4x4 matrix. And then it was covered from all the sides with lead and braided polythene of 10 centimeter each. And finally, even this 16 scintillators finally weighed about 8 tons. the weight of the scintillators was not more than 200 kilograms. But you see the enormous shielding that had to be put and to get rid of the neutrons and gammas from the reactor. And then we had to put additional high density polythene. And this is the digitizer, as you can see, just 32 cables going from 16 scintillators, and that's all. So this was the development which happened, and these are the type of spectra that we have measured. Reactor on and reactor off. Reactor on is shown in red, and as you can see, independent of the reactor on and off, the cosmic bump matches very nicely at close to 20 MeV. And this is the region of interest between, say, 2 to 8 MeV, where we are looking for the possible anti-neutrinos. And on the right side, we see the rates in our plastic scintillators. There was a data campaign of 3 or 4 months in March 2018, June, November, and December 2018. In March, the reactor was shut down for almost 22 days, whereas in the other three, in June, November, and December, it was operating almost close to 27 to 28 days on an average power of 70 to 80 megawatts. So mini Smaran is shielded, as you know, with 10 centimeter of lead and 10 centimeter of burted polythene sheets. So all these things were done, and then the data was analyzed. On the right side, you see the event selection cuts. I will not go into the details of this because they are very elaborate and need a little more, need a different lecture to understand what all we are doing. We are putting cuts on the muon, we are putting cuts on the delta T, and then multiplicity, the energy, and so on and so forth. And finally, we got, this is the result which we have got. If you can see on the table, for off, we had about 7. I'm not calling them anti-neutrinos, I'm saying anti-neutrino-like events maybe. But when the reactor was on in the month of June, November, and December, we got about 54, 55, and 43 events. Of course, with very large statistical errors, the systematic errors are still not there. And this is because we have just a matrix of 4 by 4. And once we increase this to a 1 ton, we hope that these error bars will definitely reduce. And on the third column, we have the predictions. So they do match with our measurements, but still we keep our finger crossed. We are not saying that they are anti-neutrino. We have to do some more checks before we speak it out. So now let me come to the real scenario, what is happening. Last year, we did get the supply of this 70 extra scintillators and the digitizers. So we are well equipped with all the material required to deploy it through a reactor. And all this characterization has been done. And this is just we were trying to first test the matrix of 9 by 10 in a non-reactor environment in Hall 9. Hall 9 is a separate place far away from the reactor in BARC. And it was just on 10th March, we were roping it up, and then the lockdown started. And after that, we are held up at this point. The idea was to first put the matrix here and look for the cosmological background, which anyway will be overriding there in the reactor also. So that is what the story goes. And meanwhile, even during the lockdown, our teammates have come out with the nice measurements of expected active sterile neutrino mixing sensitivity with Smaran at 3 different places within the country. The central one is the Dhruv reactor. Then there's an Apsara U reactor also in BRC. And then there's the prototype fast breeder reactor. And then they have shown here the sensitivity of this active sterile neutrino mixing and whether Smaran can detect it or not at different distances. In Apsara, it is at 4-meter distance. At Dhruv, it is at 13-meter distance. And at PFBR, it is at a 20-meter distance. And this work has been just accepted in Physical Review D. And so this is the outlook. We'll be busy as soon as the lockdown gets over to build up this matrix for cosmological background and then shift it to our reactor. And one successful operation at Dhruva has demonstrated the sprint type array is envisaged to be operated at high power reactors in Kudankulam. And because we know that Kudankulam, we have about a 3 gigawatt reactor, and we expect about 1800 events per day. It's a high power. And then Smaran at PFBR, it has got a unique core because it is a plutonium fuel, can throw some light on the various, there are some anomalies even now existing with the reactor bump at about 5 to 7 MeV of the anti-neutrino spectra that we get from the reactors. And then there are R&D activities planned of developing gadolinium doped plastic liquid scintillator in the country. Technology that cannot be imported in DAE, we would like to develop them. And we were definitely looking for underground laboratory near power reactor in Kudankulam. These are the publications which we had over the last 2 years. And this is our team. From left to right, we have Pawan, Ronnie, Vishwajit, myself, Dhruv. He is a PhD student who is submitting his thesis this month itself. His name is also Dhruv in Dhruv Reactor. And of course, Deepak and Shiba. And Ronnie is another student who has just joined last year. And so this is the team engaged in this Smaran project. And these are the oscillations. And I hope you have enjoyed it. And thanks for your kind patience.
Yes, let's thank you very much for your very comprehensive talk, with a good amount of introduction for the newcomers on this series on the neutrino field as such, and particularly the oscillation, neutrino oscillation problems and various experiments. Before you actually came to your own experiment, we are very happy that these efforts are already started paying good results. And we're also happy to see that you have shared with us a real hot result, which you, I think, submitted just last month to PRD. Congratulations to your team. And we also wish the final Ismaran detector with 90 detectors are going to come up very soon. And let us all hope the lockdown will be melted away soon, and then a big activity will start in your laboratories. So with those few remarks, let me now open the session for questions from the participants. So please raise your hands. I will take up a question at a time, and then of course the speaker will be able to answer them. Yes, there are some questions on the Zoom, but before I come there, I will look up if there are some questions on the YouTube. Yeah, there's one. This is from Shailesh Pincha. The question is on slide, is referring to slide number 40. In case of better statistics in atmospheric results, could the current results around 1000 meters infer if the data satisfies 3 neutrino case versus 4 neutrino case? So Lalit is referring to the slide number 40.
I'm at 40 now, yeah.
Yeah. So is the question clear to you, Lalit?
I don't know, please, please, I can get the question.
Your voice is breaking.
Yeah,
So do you want me to repeat the question?
Yeah, I don't heard the question at all.
Oh, okay. Well,
Hello.
I will repeat the question. Is that okay? Lalit, can you hear me?
Yeah.
Okay. The question is on slide number 40.
I can hear you.
In case of better statistics in atmospheric results, could the current results around 1000 meters, that is 1 kilometer, infer if the data satisfy 3 neutrino versus 4 neutrino case?
Well, we see there are still large statistical, large error bars there. And if we can really have the fourth flavor, yes, it should match. As you can see, beyond even up to 2000 also, it very nicely explains the fourth flavor also.
Okay.
So it could be.
Okay. The another one, okay, let me unmute. This is Ramchandran. Can you please ask your question?
Yeah. So actually, I also had I have two questions. The one is again exactly on the same point. So the 3 neutrino thing at 1000 meters. So if you see the trend, if actually it seems to be the 3 neutrino seems to be explaining better. The 4 neutrino one, actually, at least the first point is just touching the error bar kind of thing. So is there so in that sense, the 3 neutrino versus 4 neutrino, is there ambiguity there?
Yeah, but if you see the error bars, they are quite large. So
okay,
we never know and if you come very close to the reactor now at 10 meters to 100 meters, you see the error bars are still larger. But the predictions are never matching the observed phenomena. So it is just conjecture that maybe it's a sterile flavor, but we don't know.
Okay. And then
or there could be a problem in the measurement. There could be a problem in the measurements also, which we have to really understand whether it is really in a sterile effect or there is something else.
Okay. So the second one is on the what is the reactor monitoring from distance. Specifically, if you want to monitor on some hostile country, and also you cannot be going to like 9 meter, 18 meters kind of thing. So at what distance, let's say per given, let's say 1 gigawatt kind of thermal power of a reactor. So what up to what distance?
Yeah. Yeah. So I can answer this. See, when we are talking of 8 meter and 10 meter, it is basically for the sterile part and not for reactor monitoring. Now, if you have a high power reactor, you don't even have to enter inside the reactor because the flux will be so high. And that's what we mentioned that in the Kudankulam, we need not even bother about the shielding. In the reactor, we have to bother about this enormous shielding because we are inside the reactor, we are overground, first of all. So we have to put that enormous shielding to get rid of the neutrons and gammas which are already existing inside the reactor hall. But if you want to do a reactor monitoring, you don't have to enter the reactor. And if it is a power reactor, you can just place your detector somewhere outside, even at 30-meter distance. And from there, you can infer through the anti-neutrino rates, you can infer about the power operations of the reactor.
Yeah. So like what is the maximum distance you can go, let's say for a 1 gigawatt thermal, such that it is still you have some signal above the noise?
Well, this question is like how much buckets of water is there in Pacific. It depends on the size of your bucket. So it depends on the size of your detector. You can go to whatever distance you want. Increase the size of your detector.
Okay.
R square. Yeah.
Thank you.
Okay, I'm going to take one question from Mahata, but just before that, since we are talking about the size and the numbers and so on, so in your calculation, you have a detector efficiency. I think you took that as about 15%, right? Can you tell us how do you get this number? I mean, how did you arrive at your number?
That is the normal of these detectors with the type of when we are calibrating them, the type of energies we are looking into, with the typical efficiencies, and we can measure them also, the non-radioactive sources.
Okay.
But yes, the detection efficiencies are quite low. They are not very efficient detectors.
Okay. Okay. So let us take a question from Mata. Yeah.
Yeah. Thank you. This is regarding that accepted paper. So congratulations to your team. And my question is that to get that, like you said, 95% of confidence limit, how many years of data taking is required?
Okay, if you can see my slide 77, it is mentioned that the 95% confidence level comes provided in that the sine square 2 theta of 1,4 is greater than 0.09. Delta m square 41 is of 1 eV square with an exposure of 1 ton for a year.
Okay, so that with the new detail, like the full Smaran, how many years it will be required?
About a year. So the full
1 year. Okay.
Full detector is close to 1 ton now.
Yeah.
So
within 1 year.
Yes.
Okay. Thank you.
Okay. We have one more question from Aradhana. Yeah, please. Can you unmute yourself?
Hello, Dr. Pant. What are the kind of detectors they are using in the other facilities which you showed just now, Lucifer and Songs?
Yeah. So everywhere they have been using, in fact, the discovery of the anti-neutrino was through a liquid scintillator, and liquid scintillator has got various advantages, and even we would like to use liquid scintillator, but unfortunately we don't make it. So as you see in my slide, we have mentioned that we would like to develop those technologies which cannot be imported in DAE, and liquid scintillator making is one gadolinium doped liquid scintillator, because there the things will be more uniform as compared to a discrete detector that we are having. So liquid scintillator is the best option.
Okay.
But there were issues regarding to its flammability and the volume. 1 ton of liquid inside a reactor hall, which is subject to flammability. So we decided better to go for a plastic scintillator, which is modular. Modular design has its advantages, but then liquid scintillator is definitely the best one.
So how are we going to overcome those advantages? I mean, in terms of the results which we'll get.
Yeah, see what happens now when you have a discrete detector like this plastic scintillator. In this, what happens, the gadolinium is not uniformly doped inside the scintillator. It is a gadolinium foil which is wrapped on the periphery of the plastic scintillator. So until and unless the neutron reaches that periphery and it is absorbed into the gadolinium, then only it will produce a cascade. But once you have a liquid scintillator in which the gadolinium is uniformly doped, so the tau that you see that reduces. In plastic scintillators, it takes about some 60 to 70 microseconds, whereas in a liquid scintillator, it will be just about 35 to 40 microseconds. And we have to use a lesser number of photomultipliers to collect that light or photons. And in plastic, you see for 100 scintillators, we have put 200 channels of photomultipliers. In a liquid scintillator of 1 ton, you can just put some 5 or 10 photomultipliers with a large diameter, and that reduces your burden on the pulse processing and electronics also. Uniformly doped gadolinium in liquid is much more efficient than gadolinium wrapped plastic scintillator that we are having.
So you're trying to overcome that deficiency by having more number of, I mean, by increasing the size of your detector and having more number of electronic modules.
More number of?
Plastic, maybe.
Yeah, plastic detector,
no.
and then.
No, it is not that. We want basically 1 ton to have a reasonable count rate. Otherwise, if you reduce that size, the count rates will still fall down. If you can see in that table, just let me go back. So it is about, see, 55, 43. These are in some 20, 1 or 2 neutrinos per day. So if we have a 1 ton, we have about 60 neutrinos per day. So the statistical significance will improve.
Okay. Thank you.
Okay, so again, we are a little bit talking about electronics and detectors. Here is a question from YouTube by Hari Prasad. He asks, in the electronics, instead of energy measurement, can we use the time measurement between the prompt and the delayed to detect the anti-neutrino?
In fact, we are using all timing measurements only because, as you know, that this is the prompt and delayed event. So we have to decide how do you decide a prompt event. So for that, you have to again come back to the energy or the energy deposited. It's a mixture of both energy and timing. And basically, we are doing a time correlation only.
Yeah, that's right.
So the digitizers are very handy in this because they store all the information, and then offline you can put various cuts, various type of selection criteria, and then do the selection.
That's right. Okay. Okay, I don't see any more questions, right? Okay. So before we thank Dr. Pant for his excellent talk, I would like again to remind our participants about the program that we have for the next week, which is week 11. We have essentially 3 talks now, again going back to regular now that the Neutrino conference is over. So we have Monday, Wednesday, and Friday at 6 p.m. And the next week, on Monday, we are going to have Dr. Subhashri Chattopadhyay from VCC talking on study of strongly interacting matter under high temperature. Talking on Wednesday is Professor G. Rajshekharan, hundreds of years of fundamental physics and a crisis. And we are going to wrap up the next week, that's on Friday. This talk is going to be one of the INO students, past students, in fact, the first batch of INO training school. Dr. Vivek Singh is going to talk on neutrino and particle physics with low temperature detectors. So this is the program for next week, and we invite all of you who are on call today to come back to attend these interesting talks as they are before. So with this, on behalf of all of you who are online, let us thank today's speaker, Dr. L.M.Pant, for his excellent talk, and also let us all wish him and his group very successful Ismaran, and hope to again have another talk from him soon on the results of the full-scale Ismaran. Thank you very much, Dr. Pant.
Okay, thank you, Dr. Satyanarayana, and all the one who were there in the audience. And thanks a lot. It was really nice interacting with you all. And we hope to come up with further talks as with our measures.
Okay, so thank you then. Take care. Stay safe. Good night, everyone.
Bye.